Let's do another example of classification. This time I've got a data set from some researchers who were studying how to detect counterfeit banknotes. So they wanted to build a mobile app for your smartphone. They would let you take a picture of a dollar bill, and they were hoping that the app could predict whether or not that bill was counterfeit. So it sounds like a perfect setup for classification. We have a yes or no question we want to answer. Is this bill counterfeit or legitimate? And they have a historical data set. They were able to obtain a large collection of bills, some of them counterfeit and some of them legitimate. And then they took pictures of each one of those and then proceeded to use machine learning to try to learn the patterns, what patterns tend to characterize counterfeit bills. So we're looking here at their data set. You see in this table, there's something like almost 1,400 rows. That's about 1,400 different examples that they had collected. And what we see in this table is 5 columns. The last column, the class, indicates whether the bill was counterfeit or legitimate. There are 2 types of bills. 0 indicates legitimate and 1 indicates counterfeit. In machine learning language, we call that the class. And our goal, given a bill, is to classify it into one of these 2 classes. That's why it's called the class. The other 4 columns are some kind of properties extracted from the picture. Somehow they took the picture of the bill and they got 4 numbers out of it. I don't really understand how, but they got it somehow. I don't know what they mean, but I guess they're relevant somehow. So those are called those 4 are called attributes. Each bill has a value for those 4 attributes, and we're going to use those 4 attributes to try to make a prediction about the class. The attributes can be extracted from the picture, and then hopefully our classifier will come up with some smart way to predict the class, whether or not this bill is counterfeit based on those attributes. So when I had this data set, the first thing I did was I started to take a look at it. I started to visualize it, explore the data set, and get a feeling for what's in there. And I did that by making some scatter plots. So let's make some scatter plots here. I started by picking 2 of these attributes and making a scatter plot to show all the data points. And on the x-axis, I show the first attribute, wavelet var, whatever that is. And on the y-axis, I show the other attribute, wavelet curt, whatever that is. Okay, so each point in this picture represents a bill in their collection of historical bills. The blue ones are legitimate and the yellow ones are counterfeit. And as you take a look at this picture, you can start to see some patterns emerging in this. It looks like these 2 attributes are at least somewhat helpful in predicting, identifying counterfeit bills. For instance, over on the far right, we see mostly blue. So if we get a new bill that falls in the far right, probably we should guess that bill is legitimate. In the far left and up at the upper left top, we see lots of yellow dots. So if we get a new bill that falls in one of those regions, it'd be natural to expect that bill is probably counterfeit. So you can start to see some patterns like this in the data. And if you imagine using the nearest neighbor rule that we described in the last video, you could use a nearest neighbor classifier to make predictions about new bills you run across given this historical data set. So let's take an example, a very simple example. If we had a new bill that showed up on the scatter plot kind of here in the middle, what prediction would we make? Well, we would find the closest point in this scatter plot. The closest point is just a teeny bit to the left, and we look at the color of that closest point. That closest point was blue. It's class 0, meaning the closest point was a legitimate bill. So what that tells us is that the most similar bill in their collection was legitimate. So probably this new bill we're looking at right now, probably legitimate too. At least that'd be a natural prediction. On the other hand, what if you saw a new bill and you're wondering whether it's legitimate or counterfeit? We counter this new one and it's up in the upper left area. How would we classify that? Well, the nearest neighbor rule says find the nearest point. The nearest point might be a little bit above it. That's a yellow point. That's a counterfeit bill in the collection. And so if the most similar bill in their collection is counterfeit, then probably this new one, our best guess would be that it's counterfeit too. So far, that seems pretty straightforward. If you think about this rule a little bit, you might be a little bit unsettled by the overlap. There's kind of a clump of blue on the right and a clump of yellow on the left, and they have some overlap. These clumps have an overlap. What does that mean? It means that if we had a new bill that falls somewhere in that middle of that overlap, well, what's the nearest neighbor to it? The nearest neighbor to it, it's hard to say. The nearest neighbor might be one of the yellow points, in which case we'd make a prediction of counterfeit, or the nearest neighbor might be one of these blue points, in which case we might make a prediction of legitimate. And exactly where this new bill falls will determine which one's the nearest. But in any case, what this overlap is indicating is that there's some uncertainty in our predictions, especially if the new bill falls in this overlapping region. Then it's hard to be sure. Now, in classification, we can't answer the question, is this bill counterfeit or not? We're not allowed to say, I don't know. We're forced to make a prediction. And so, especially if the bill falls in this overlap region, we're forced to guess. We're forced to make a prediction, and our prediction might be wrong. And because there's a fairly large amount of overlap here, that could lead to a significant error rate. For instance, if you had a very simple classification rule that said, I'm going to draw a line, and everything to the left of that line I'm going to classify as counterfeit, and everything to the right of that line I'm going to classify as legitimate, that'd be a plausible classification rule given this data set. But of course, that classification rule would have some errors because there are some legitimate bills that are to the left of that line, and there are some counterfeit that are to the right of it. So this is just something to be prepared for and get comfortable with, that classifiers won't always be right. They're making predictions, and they may have some error rate. So we evaluate a classifier by how accurate it is. How many errors does it make? And we're looking for the most accurate one we can find. So what this tells me is that this pair of attributes, wavelet var and wavelet curt, are pretty helpful at predicting whether a bill is counterfeit, but not perfect, maybe not even great. They give me some prediction, but I was kind of hoping to do better than that. It doesn't look so good for their mobile application. The mobile application is going to make a lot of errors. So I started graphing other combinations of attributes, and I started to see the same thing with every pair of attributes I looked at. There was this overlap, and I started to get a little discouraged. So, for instance, we could take a look at another pair here. This pair is a different pair of attributes, wavelet skew and entropy, and we get a picture that looks like this. Whoa! There's quite a lot of overlap between the blue clump and the yellow clump. And if I had to write a classification rule, I'm not sure what I'd do. Maybe I would kind of draw some kind of line up like this and say everything to the right of that line is predicted to be legitimate and everything to the left is predicted to be counterfeit. But gosh, that rule would make a bunch of errors. There's a whole bunch of bills in their historical collection that were legitimate but that are on the other side of the line. And the nearest neighbor classification rule is going to make a whole bunch of errors too. For instance, well, yeah, it seems pretty clear that stuff in the middle in this overlap could easily end up getting an incorrect prediction, because you can see the blue and the yellow are overlapping, and there might be a legitimate one whose most similar point just happened to be counterfeit. The most similar in the historical data set happened to be counterfeit. When you're in a region with a lot of overlaps, there might be a similar one might just happen to be counterfeit or might happen to be legitimate, and so your classifier could easily make a lot of errors. So I was starting to feel a little discouraged when I saw these pictures, because it looked like any pair of attributes I looked at and I could make some prediction, but that prediction wasn't going to be super accurate. And sometimes this happens. Sometimes it turns out that your classifier, you just don't have enough information in those attributes to make a very accurate prediction. Sometimes it happens that if you only look at one or two of the attributes, one or two of those attributes is not enough. And in this example, I found this example particularly interesting because no two of the attributes is enough to make a good prediction. But if we use all of the attributes, all four of them, in fact, it's enough to just use three of them. We don't need the entropy if you use wavelet skew, wavelet var, and wavelet Kurt. That's enough that you can make a very good prediction. So here's a 3D scatter plot. It gets a little harder if I want to look at three attributes, because now I need 3 dimensions, but here I've got it. On one axis is each of these 3 attributes, and here's a scatter plot in 3 dimensions now of where all of the data points in their historical data set lie. And maybe you can't quite see it, but there actually now is a clear separation between these 2 clumps. There's no overlap, okay? Which is kind of fascinating. It means that if I use information in all 3 of those attributes, I can build a classifier that does a very good job of predicting. My classifier rule might take a plane that separates these 2, and depending on which side of the plane you're on, it predicts you're either counterfeit or legitimate. Okay? So this is a situation that can happen where if you look at any 1 or 2 attributes, they don't have enough information to make a good prediction. But if you look at all of the attributes, you can make a very good prediction. This also illustrates that things are quite tricky to visualize when we have many attributes. And this comes up a lot. Often we have many more than 2 attributes. You can see with 2 attributes, I could make a scatter plot that made it easy to visualize. With 3 attributes, 3 dimensions, you can still pretty well visualize. But what if there's 4 attributes? I'm not going to make a 4-dimensional scatter plot. And what if there's 50 attributes? So what this illustrates is we're going to need a rule, a classification rule, that does not rely on us looking at a picture and coming up with a rule ourselves. And that's what the nearest neighbor classification rule gives us. It's a way that generalizes so we don't have to come up with the rule. The computer learns the rule. And it works no matter how many attributes you've got. So in the next few videos, we'll start to dive into how do you implement a nearest neighbor classifier, how do you evaluate it, and we'll look at applying it to some more interesting data sets.